Hello, welcome to Unit 3, Energy. Today, we're going to be taking a look at a couple of the main points within this unit. Specifically, we're going to be seeing the two fundamental skills for this unit. These skills are ones that are vitally important, and you cannot get by in this unit without knowing how to do them. They are ones that I think you'll have a lot of success with today, and we're going to talk through how to do them. The two skills are energy identification. What this means is which kinds of energy are present at any particular moment in a situation as you look at what's happening. And the second one is using energy formulas. And we're going to plug numbers into them, do some basic math, and just solve things for them. It's the equations I think you won't have much trouble with either. So let's get started by talking about the different types of energy. There's going to be three main types of energy we're going to be talking about in this unit. There are a few others that we'll see in here, but we're going to start off with the basic three here today. First one is kinetic energy. You're well aware of what this one is, I think. It has to do with the motion of objects. The second one we're going to look at, you may call this potential energy, but I don't want you to call it that. It's the gravitational energy. You can call it gravitational potential energy, but if you just call it potential energy, that will be wrong. So make sure that you are talking about it that way, because there are a lot of different types of potential energies, and so just saying potential energy is not specific enough. You're going to have to say gravitational potential energy. And hopefully you understand and got the idea. This is associated with objects being up high, elevated. If something is up high in the air, that means it's going to have a lot of gravitational potential energy. We'll talk a little bit about the things that contribute to this in a little bit as well. And then our last one would be either the elastic or spring potential energy. So you can talk about that one as either EP or SPE. I think in these notes I'm calling it spring potential energy, but it would also be true for a rubber band. So like if you stretched a rubber band and point at somebody, the reason why you feel kind of startled or afraid when somebody stretches a rubber band at you is because the rubber band has elastic or spring potential energy. It's got a lot of energy that then if they let go of it, it's going to start flying at you, and it might hurt you if it hits you in the face. And so those are the kinds of energy we're going to talk about. And so that's the energy of stretched or squished or compressed, if you want to use a more technical term, objects. And so we can look at these and we can come up with some information based on that. All right. So how can you tell if a certain type of energy is present? We're going to ask ourselves some questions. The first one is, well, if we wanted to look at kinetic energy, which we're going to abbreviate as KE for kinetic energy. And then we can say, if something's moving, yes, we've got kinetic energy. If nothing's moving, then no, there's no kinetic energy. The next thing we can look at is, well, what about for gravitational potential energy? For our GPE, well, we can say, is anything up in the air, up high? And so whenever we're doing this, we're going to have to pick somewhere we're measuring from. We call that our reference level. And so most of the time that'll be the ground, but we ask, is anything up above the reference point? Or, maybe we'll look at like the bottom of the table that everything is on, and we'll see, is it up above the surface of the table? And if it's up above the table, then that means it's above the reference point. As we say, is there anything up high, up above the reference point? And if there is, then we've got gravitational potential energy. And then for the last one over here, it's the spring potential energy. And so you can tell if that's present based on if anything is stretched or compressed, like a spring or a basketball, like as it bounces off the ground, it gets squished a little bit. And so that would kind of fall into the same category of spring energy or elastic energy. And so these are the ways we can tell if a certain kind of energy is there. So we're going to look at some examples, and I'm going to ask you to kind of follow along and see if you can figure out the kinds of energy that are present at any given moment. And we'll kind of have you pause and see if you can answer the questions, and then I'll tell you the answers. Kind of simulate what we would do in class if I was there today. So here's a situation we're going to take a look at as we do this practice for this primary skill. And as you kind of see this, what we'll wind up doing a lot of times is see, like, starting here at point A, then going to point B, then going to point C, and asking ourselves, what happens with this? What happens to the energy from the beginning to the middle to the end? What kinds do we have at the beginning? What kinds do we have in the middle? What kinds do we have at the end? And by doing this, by asking ourselves this question over and over again, we can sort of visualize what's happening to the energy. Where does it start? Where does it end up? And by doing that, it's going to help you be successful in this unit. So this is a skill and a thing you want to practice with every single problem is, how do I start? Where's the energy start and where does it go? And so what we can look at here is at point A, what kind of energy do we have? We'll ask ourselves the same questions. Is anything moving? And we're looking specifically at the ball, in this case, the green object. Is anything moving? And hopefully you can say no. Is anything up high or above the reference level? Which you notice over there on the side, it says reference level in blue. That means at the ground, that's where we're going to consider it to be at the reference level, have no height. So it is, it's above the reference level. So that means it's going to have gravitational potential energy. And there's no springs or anything, so there's no spring energy. Then halfway down at point B, look at this. Is it moving? Yes, it's definitely moving. Is it up high? It still is up high. So at this point, it's got gravitational potential energy and kinetic energy. It's got a little bit of both. Maybe if it's halfway down, it's about half and half. And then down at the very bottom, now, is it moving? Yes, it's definitely moving. Is it above the ground? Is it above our reference point? No, it's at the reference level. Or maybe, technically it would be very, very, very slightly above it. But we're going to consider that to be, no, it's not above the reference level. It's all going to have kinetic energy. There's still no springs, so we don't have any of that energy. So this is the way we would do this. We'd look at each of the points, each of the locations, start and end, or A, B, and C, and identify what kind of energy is present at each spot. And that's basically the whole thing we're doing right now. Later on, we'll actually look at numbers and values for this, but right now we just want to identify, is this energy present? And if it is, are there any other kinds of energy that are present? And sort of where does the energy go from as it goes? So at the beginning, it's all in gravitational. At the end, it's all in kinetic. And in the middle, it sort of switches from one to the other. All right, here's another example, A, B, and C. I want you to pause the video and see if you can write down what is the amount of energy at A, B, and C, or at least consider it, and then unpause it and we'll talk it through. Okay, let's take a look. So at A, the ball is up high. So that means it's got gravitational potential energy. At B, the ball is moving. So it means it's got kinetic energy. And what about gravitational potential energy? Well, it isn't at the reference level. It's not at the point where we're measuring from. If you wanted to, you could sort of, for a problem in the future, we'll decide where the reference level is, and you could put it up there at the lowest point. But for this problem, it's not. The reference level is actually down here, below this point. And so we're going to say that because it's above the surface there, it still has a little bit of gravitational potential energy. And then over at point C, it reaches the highest point again, and it stops, and it's got all gravitational potential energy again. All right, for this next one, I guess I've kind of given this one away. We've got gravitational potential energy at the beginning. Halfway down, it's gravitational and kinetic. And at the bottom, it's all kinetic energy here. And for this one, let's see. We got the beginning and the end. And we want to know, is there any kinetic energy, gravitational potential energy, spring potential energy to each of these points? Take a moment and think about it yourself. Pause it here. Then we'll go on. All right, so at the beginning, when the student has the slingshot pulled back, what kind of energy are we sure we've got? I think that's going to be spring energy for sure. And is anything moving? No, so we don't have any kinetic energy. What about, is it high up? Well, it's above the ground, but in this problem, you notice the reference level is right where it is. So it's at the reference level. We're going to consider that being where we're measuring the height from. And it's not above the reference level. It's just right on the reference level. So we're going to say no gravitational energy, but there is spring energy, spring potential energy. And at the end, we got to think what's going on here. Well, the object's certainly moving, so we've got spring energy, or we've got kinetic energy, and it's still at the reference level, so we're going to say no gravitational energy. We're not going to consider that here. And the last one is spring energy. Well, spring energy was kind of, they're no longer pulling the slingshot back, and so the spring energy is gone. So those two are gone. It's all kinetic. So it's all spring at the beginning, and it's all kinetic at the end. Got one more for you here to take a look at. Maybe there's two more, but one more to practice right now. Take a second. All right, so at the beginning, the initial, it's when the crane is pulled back, and then when we let go, it swings down and hits the building. So it starts off with gravitational potential energy, and it ends up with kinetic energy, but still gravitational potential energy because it's also still above the reference level, above the ground. All right, and our very last one here, this is a cart with a plunger inside of it. When you push that little button on it, it shoots the plunger out the back and it pushes off the wall. And the cart then goes flying off to the side. And so that's what we're going to look at and think about. So pause for a moment and see if you can identify the energy at the beginning and the end. All right, so at the beginning, all we have is spring energy. Because the energy is in the spring, it's not elevated, so we don't consider gravitational energy unless something's moving up or down at some point throughout the problem. If it stays at the same level the whole time, we just kind of ignore the gravitational energy because it's not changing. And then as it goes along, at the end, it's all in kinetic energy. And so it started off at spring energy, it ends up as kinetic energy. Oh, and this one I sort of got in the way a little bit. We got here A, B, C, and then D down here is back behind my little scribbles. And this person, they sort of stop down here all the way at the reference level. So give yourself a second and see if you can identify the kinds of energy at each of these spots. All right, so at point A, they're up at the top. They're about to go bungee jumping off the bridge. And so we've got here gravitational potential energy only. At point B, now they're starting to fall down, and they've got gravitational potential energy and a little bit of kinetic energy. Now, I'm not going to say this is spring energy yet because they haven't reached the point. If you look over here at the beginning, the string only goes down to this sort of dotted line that's there. And so they haven't gotten past that, so it hasn't actually gotten stretched out yet because the bungee cord can only get like stretched out once it passes there. So at B, they have not gotten any spring energy. But at point C, they've got a little bit of all three. They got kinetic, gravitational, and spring energy. And then down here at the end at point D, this is when they stop at the lowest point. At the lowest point, we're going to say there's no gravitational, and they've stopped, so there's no kinetic, and that means we only have spring energy down here at the bottom. All right, so this is our practice for identifying different types of energy. What we're going to look at next is the second skill, and this is the one that we're going to get a lot of practice with today. So there's going to be a WebAssign where we just do a ton of these kinds of questions. So I'm going to talk through a few of these now, look at the formulas. We'll start off by giving you guys the formulas for kinetic energy and gravitational potential energy. Here, the equations of the formulas. So here are the two formulas that we have. For kinetic energy, it is that Ke kinetic energy is equal to 1/2 mv squared. And hopefully this makes sense because kinetic energy has to do with mass moving. So it has to do with the speed and the mass. So more mass means more kinetic energy, more velocity or speed means more kinetic energy. And hopefully that makes sense just sort of thinking about it. And then for the gravitational energy, it's the same sort of idea, is that we can get more gravitational potential energy by lifting an object up higher. And so increasing the height would be one way to do it. So, if I hold a bowling ball a couple inches above your hand, or I hold a bowling ball a few feet up above your head, you might have a different reaction to that because there's more energy with it up higher in the air. Also, if I hold a baseball, like a tennis ball, up against the ceiling up above your head versus a bowling ball up against the ceiling above your head, you'd be more uncomfortable with the bowling ball hanging there because it has more energy, it has more mass. Also, if you're on a different planet with a different value of G, which on Earth it's 9.8, just as a reminder, then it would have more or less energy depending on which planet you're on. But we're going to deal with Earth here because most of us have been on Earth for most of our lives and probably will remain there for most of our lives. But I don't know, maybe the future will turn out differently. All right, now what we want to do is use these equations, utilize them to answer questions. And at the very beginning, these are kind of pointless questions, but it's just asking questions about the energy. And we're going to solve for all of the variables involved using both of these equations. Make sure that we feel like using these equations is super easy and we can do it without making mistakes over and over and over again. That's the goal for doing this here today and using these throughout the rest of the unit. Because if you can use these equations without having to really think about it, it'll make the rest of the problems in this entire unit where you're using these equations over and over again easier for you. All right, here's a problem. A 15 kilogram car is traveling at 10 meters per second. What's the kinetic energy? So for any of these kinds of questions, we want to think what's the formula we're going to use and what are the variables that are involved. So let's take a look. Here I identified 15 kilograms is the mass, and that the velocity or the speed is 10 meters per second. I'm looking for kinetic energy, so I'm going to use the kinetic energy formula, 1/2 mv squared. And for this, all I'm doing is plugging and chugging. We're just putting in the 15 and the 10 in the spots that they're supposed to go. So it's 1/2 times 15 times 10 squared. And if you type that in on your calculator, you'll get an answer here. Kinetic energy is 750. Now the question then might be 750 needs some units, right? 750 what? Well, the unit that we have for energy is called the joule, and we use a capital letter J to denote this. The unit for energy is joules, Joules, or Joule for 1 joule, or 10 joules, you'd plural it. And the symbol we use for it is a capital letter J. So whenever you see energy, that's what you're going to put in as the unit. If you got this on the WebAssign, capital letter J for energy. If you're finding for mass or speed, you'd use kilograms or meters per second. All right, so let's see this one more time in action, finding something having to do with kinetic energy. But rather than finding the kinetic energy, let's assume we know the kinetic energy. So if we've got a baseball 0.143 kilogram ball, and it's got 28.6 joules of kinetic energy, and we want to know how fast is it moving. So this is a good time for you to pause the video, write this out, or you don't have to write the whole question out, but write your work out. See if you can calculate how fast is it moving. If you can do that, you're ready to move on to the next step. I'll show you here in just a minute though. All right, hopefully you wrote it down. I'm going to write down the things that I know from the problem. See the mass there. I see the kinetic energy, 28.6 joules. And I want to know how fast is it moving. It's in meters per second. And so I'm going to do this calculation. I'm going to write down the equation. I'm going to plug in my numbers where they go. And then we're going to do a little bit of algebra, or a little bit of arithmetic and algebra to get this through there. Multiply both sides by 2, cancel the 1/2, or you can multiply out the 1/2 as you go, like however you want to go about doing this. I've got right there, and then I want to solve for v. So I'm going to solve for v squared. And v squared is equal to 57.2 over 0.143. And since that's v squared, I want to know what actually v is, the speed. So I'm going to take the square root of both sides. And I get this. If you type that in on your calculator, you get 20 meters per second. So that is our second question with using the kinetic energy formula. So what we're going to use now is, what about if we wanted to use the gravitational potential energy formula? We're going to go through this. And so you might want to pause here and see if you can do this one. This is a pretty straightforward question, but hopefully you can identify the variables that are involved. These two specifically and what those mean. So I'll say, all right, 6 kilograms, that is the mass, 7 meters, that's the height, and we want to know what's the gravitational potential energy. So I write down the formula for that. Now we know the mass and we know the height, but we got to remember, oh yeah, we also need to know G. Hopefully remember on Earth, 9.8 meters per second squared. We can just throw all the numbers into the equation and get ourselves a value. 6 times 9.8 times 7, and we get 411.6 joules of gravitational potential energy. That's how much energy it's got. All right, this is the last one I've got for you in this video. It's a calculation to look at the mass, using the mass and the gravitational potential energy, how high up is the piano? And there's an assumption here that it's on Earth. So give yourself a second, see if you can solve this one before I talk through it. All right, so I'm identifying the variables. I've got here that the gravitational potential energy equation is mgh, mass times gravitational field strength on Earth, times the height. And the variables that I know out of all 4 of these, gravitational potential energy, mass, g, and h, I know some of them, and I'll fill them in right here. And I'm looking for the height, so I don't know what that one is in this particular case. But I'm going to plug everything into the equation in the spots that I know. I've got GPE goes in here, mass goes in here, and G goes in there. And if I just do a little bit of algebra solving for H, I get 63,000 over 1960, which if you type that in on your calculator, you get 32.14 meters. All right. And then the last thing about this, for each of these equations for kinetic energy, we just showed an example of solving for kinetic energy and solving for velocity. You could also solve for the mass. And for gravitational potential energy, we solve for GPE and height, but you could also solve for the mass. Or if you were on another planet, I could tell you the other three variables, and you could solve for the strength of gravity on that planet G. These are some of the ways we're going to be using these equations, solving for any variety of different things. So you just have to sort of pay attention to that as you're going through this stuff. Also, another thing you can do with this is if you have a thing that's flying through the air and moving at the same time, you could calculate both the kinetic energy and the gravitational potential energy. You can add them all together. And maybe if there was spring energy too, you could calculate all three of those and add them all together. Today we're going to get a bunch of practice using these two equations. So work together with your groups. You're going to have different numbers, but the same kinds of questions. See if you can go through them. There's a couple questions in there that are a little trickier, but you should be able to be successful in answering quite a few of these as you're working on them today. So do your best with it. Anything you don't finish in class, you should try to finish up next time. I think there's 2 questions in there that I will note in the agenda for you as like, those are like next steps, challenging problems. And so we'll talk about those a little bit more when I get back next week. So good luck with all of this. You've got that web assigned to do, and then it's just up to you to, do what you need to for the rest of class. Have a great time. See you next week.